Hi everyone, this is Lun Lam. Welcome to the AIRS in the Air Multi-Robot System Lecture Series. And this is the second day of this series, and we are honored to have two famous scholars join us today to share their insights on the latest developments in multi-robot systems. And they are Professor Sebastian Scherer from the Carnegie Mellon University and Professor Moju Zhao from the University of Tokyo. I hope you find this lecture informative and engaging. Today, we also have Dr. Tianwei Zhang to help hosting the talk. Dr. Zhang also received his PhD degree from the University of Tokyo, and he is currently a research scientist at AIRS. His research interests include dynamic environments lab and humanoid robots. All right, Dr. Zhang, over to you.
Hello, everyone. I am Tianwei Zhang. I will host this talk today. So today our main topic is about multi-agent robotics, and it's our honor to invite Professor Sebastian Scherer from the AIRS lab of CMU, one of the most famous robot vision lab in this world. So he made a lot of impressive things in path planning and challenging environment perception. So let's welcome Professor Sebastian to start his speech.
Okay, hi everybody. Thank you for the opportunity to let me give this talk today. And I'm sharing my screen. I think you can see the screen, right?
Yes, we can.
Okay, great. So I'll get started. So today, thank you also for the introduction. We do lots of work on perception and SLAM, but today I want to take the chance to dive a little more into some of the work that we're doing on the planning, intent prediction, and how we try to coordinate these. So just to start off, just on a high level, the goal of our lab is to build autonomous systems that can survive in the wild, and in this particular talk, we'll focus on planning. Just to give you kind of an idea of the types of situations we look at, here's some of the results from the DARPA Subterranean Challenge, where we had these ground robots and drones exploring underground spaces. And so the question that we're trying to, one of the questions we're going to look at today is, how do we look at this exploration? For example, how do we look at information gathering? And just a little more on the high level, like what is the type of method and how could you solve this problem? So I'll not. So first I'll give a little bit of an introduction on what is the planning problem. How can you think about planning, especially for the types of systems that we do? And I'll talk a little bit about informative path planning, exploration, and then social navigation for flying, which is a little bit of a different topic, but I think will still be interesting to you, and then some inverse reinforcement learning for off-road driving. So on the very high level, kind of diving straight in, you could think about this problem as a variant of the optimal control problem. So we're trying to find the best trajectory. So in this case, often we look at X, Y, Z and heading, for example, for a drone. We have potentially some initial and start states. Sometimes you don't know what your start end goal is. And you have some non-holonomic constraint system limitations, and you might have some limits on your cost function as well. So let's take this kind of one step at a time, and first look at, for example, the system. So let's say we have something like a helicopter. In this case, you'd have some non-holonomic constraints, which mean that an input doesn't directly change one of the dimensions on the very high level. So this means, for example, you can't instantaneously turn. Other things we often will have are system constraints. So, for example, you might have a limit on your heading rate. And so once you have your system, you know how you can go from one state to the next. Then the next part is how do you find the best path? And so there are many ways you can define this. Sometimes you look at this as a sum of weighted objectives. For example, a popular one is time to mission completion. So you want to find the shortest time. It could be you don't want to enter some polygonal region, or another popular function that's a little more complicated is time to collision. So we would say, okay, how much time does it take me to collide with an obstacle? And there's some ways you can make that calculation. Is typically expensive, but there's some approximations that allow you to make this fast. So let's say we have this type of problem. How can we solve this type of problem? So let's look at an example. Imagine we have a helicopter and we have an obstacle and a goal point and a start point, and we want to find the best trajectory. And so, and the other constraint that we have to think about that's often neglected is that we want to do this in a limited amount of time. So we sense these obstacles, so we only have we have to find these options in a certain time limit. So one way to abstract this problem is to think about this as a graph, right? So we would we have a start and an end state, and we create other vertices, and then it's really about the question. The question is really which vertices do we create and which edges between vertices do we create. And so how do we define an edge? And so one way to look at the edge is, for example, to calculate how close does it get to an obstacle. So for example, in our case and for flying often, the objectives are a little more complicated than for driving, because you want to stay away from things if you can, rather than just avoiding something, right? For driving, you have to stay on the road. You don't have a lot of space to kind of optimize in, while in flying you have a little more trade-offs. And so for an edge, you typically accumulate the cost of the objective function along the edge. And you can imagine that depending on the complexity of the objective function, calculating those edges can be expensive. And so let's say you have a limited amount of time, let's say 100 milliseconds, and in those 100 milliseconds, you can create a certain set of vertices and edges, and check a certain set of edges. And so then the question is, where should you put your graph? What resolution should you pick? Which edges should you create? And so that's a lot of the challenge of real-time planning approaches, the type that we would run on an algorithm where we have essentially an anytime requirement. So after some certain time, we need a solution. So one type of approach that is very popular is to construct a tree to find a path to the goal. So, for example, a method called RT star. So again, we abstract the start and the goal, and then we sample potential locations to add new vertices to our tree. So we'll add an edge to our graph, add a new vertex, and continue this process. And so there are some nuances about how you guarantee optimality, but I think that there's not as important right now. The idea is really to think about this, how start my, okay. Sorry, that's a request to start my video. I don't know, maybe it turned off. There's a, how you construct this graph and then search it. And so let's look at some examples of this type of approach and how we look at this in practice. So first, let's look at this informative path planning problem. So in this problem, we want to maximize the information gathered by respecting budget constraints. So to put it in another way, we have a limited amount of flight time, and we want to maximize the information we gather. And similar to the picture before, you can see in this animation, we're calculating a graph and then trying to find the best path on that graph. And as you can imagine also is here we don't have a particular goal point, right? We don't want to go somewhere. We're just trying to maximize the information given this objective function landscape. And so this is a pretty common problem in many different applications. So you can think about inspection, reconnaissance, wildfire, trying to estimate wind fields or other environmental factors, search and rescue, many of these applications. And so, like we discussed before, people have looked at this in many different ways. So one approach is to construct a fixed graph. So that's the picture on the left here. So you're explicitly constructing this regular graph and then searching on this graph. In the middle, the method is essentially a one-step method. So you're essentially just creating the next vertex that's best using the gradient of the cost function, for example, and then going to that, executing that next action, and you keep continuing this. Or you could take this approach on the right, which is sampling a tree. And which method is the best often depends on the structure of your cost function that you're trying to optimize. So in this method that we call Tigris, what we are trying to do is essentially maximize the information given this motion model in something that's limited compute, works on an embedded computer, and is fast enough and can find a path for the entire project. And so you can see, I'm not going to go through the details of this algorithm, but you can see that it's essentially constructing this tree on the fly, and a lot of the interesting parts come in is where do we expand edges to? We want to really only expand them to places where we think we'll actually get some information, so not create a tree in situations where in directions where we don't actually think we'll get anything. And then also be efficient about calculating the cost function. So as you saw in the video, as you're sensing a camera image, you're carving out essentially areas that you have seen and gained information. And you could imagine that if you just take this camera frustum and then ray traced out all the cells in this grid, that would be an expensive operation. So calculating the reward of that edge would be expensive. So there's some optimizations we do to make that fast. And so we've also shown that this is better than this current state-of-the-art method. And so then the next question then is, okay, so you can do this once, but in practice, you keep replanning over and over again as you keep exploring, because your vehicle might not do exactly what you think it should be doing, or you're sensing getting some new information, and so that new information will change what the best path is. And so what we do is we recycle the tree from the previous plan and update to predict to help us get a better tree for the next search. And so this tree recycling can be very efficient. And so we've also tried this in an actual experiment, and so we were trying to find fires. Was the objective. We had these two priors with these two areas, and so then the drone went out and had a downward facing camera and was trying to look for these fires. Now, in other situations, you might not have, so in a wildfire situation, it might be a pretty static situation where your objective function essentially stays in one place, but sometimes you might have more dynamic situation, where if you have people or cars or something like this, wildlife running around. And so you want to know, okay, how will they behave in the future? And so what we do there is actually have a separate representation for these dynamic targets. So once we have detected them, we predict their future motion based on a particle filter, for example, or you could also use other representations, such as a Kalman filter or Gaussian mixture model. And so now your planning space actually increases by time as another dimension. And so since you're adding now time, planning can become very slow. So to help with this, we are trying to learn what are valuable future states using Monte Carlo tree search. And so that Monte Carlo tree search essentially gives us an end cost on how much we will information will gain by going to a certain spot. So this is kind of a quick summary of some of the work that we are doing on informative path planning, and this type of approach, has often many trade-offs. So the examples I showed you, you have several sparse things you're looking for. So it could be some people, for example, in a big area, and so you have some coarse information about where they are. And so in this case, the Tigris method would perform very well. If you have a lot of targets you're trying to find, a method that just greedily goes for the best next area where you can gain information might be much better. So there's not one size fits all approach that really can optimize everything, because a lot of the performance depends on the objective function and the shape of that objective function, and algorithms to gain speed make approximations and use heuristics to try and come up with a good search of that space. So next, we're essentially going one step further. So in the previous example, this cost function was fixed and given to us, and we didn't know if we actually see something, how much information are we going to gain. And so this is a classical problem in robot exploration, where the question is, let's say you have these three possible goals, which action will get me more information in the future. And since you have a limited sensor horizon, you don't necessarily know which action is the best one to take. And so what we're trying to do here is to try and predict how much value there is in these future potential goals. And so the input are these voxel grids, and the projected images are essentially how much information you've already gathered or is empty. So green and white is this green are areas that are covered with the camera, white are areas that are seen geometrically but are not have not been seen by a camera yet. So our LiDAR has a longer range than the camera does. And so we'd learn this value function of where we predict how much state is worth. And then when we use this method online, we adapt the weights on the fly as we explore, because once we actually get to a location, we know how much information we have gained from that location. And so we performed some experiments with the sub-T robots. And these are some snapshots of the environments that we tested the method in. So some urban, some caves, some mines. And then looked at the data set to see, okay, how much regret do we have? So if you choose a goal that is suboptimal, we'll essentially miss some reward, and that's what we define as the regret. So if we look at a sample run, one of the robots, so blue points are the ones that are seen by the camera, white are points that are seen in the geometry. And so in this example, the blue ball is lower value because already a lot has been seen, and the reds is on higher value because it's an area where the robot has some geometry but has not seen with the camera. And so these spheres are actually generated somewhat randomly and then evaluated. And we compared this to some other methods and showed that this works pretty well. Let's see, it shows. So here's some comparison between our method and our previous method, which is the method we used in the sub-T challenge. And so in that method would, for example, sometimes skip these rooms because it did not think there was a lot of information there. And so with this new approach, it can find some of these spaces. And we did some experiment with some other data sets, with other methods, and there we also get more coverage. Okay, so these are kind of two methods looking at this more on the information gathering side. You know, how do we explore this space, or how do we gather information? And how do we predict where information next is? So next we'll switch gears a little bit, but it's going to be more about multiple agents interacting. And so the problem that we are interested in is trying to fly like a human in shared airspace. And so the motivation there is when you have more of these large drones, you can think about these urban air mobility or advanced air mobility vehicles or large cargo drones or something, several thousand kilo heavy drones that carry people. These drones will have to interact with other helicopters and small planes in the same manner. And so we want them to behave in an expected way, the same way a human would fly. And what we are looking at is to not just look at the data, but also encode the rules of the air. So we've been collecting data at 2 airports here in Pittsburgh. One is an untowered airport and one is a towered airport. And we get the actual trajectories of the aircraft, radio and weather information. So this diagram on the top left here shows you how aircraft typically fly. So depending on the wind, they might land on, so in the middle here is the runway. And so they essentially fly a racetrack around the runway before they land. And so they can come in from any direction and then they'll enter this racetrack pattern and then come in and land. And so in this example here, untowered means that there is no control tower. So it's essentially just the pilots talking to each other and saying, hey, I'm coming in to land. And the other person says, oh, okay, I'm also coming. And then they have to deconflict themselves. So the way this looks like is, for example, somebody might be in this pattern and then somebody else comes in. And so they'll have to, figure out how to sort themselves in. You can think about this is basically the same thing as merging on a highway. And so we want our system to follow FAA guidelines in addition to behaving like people actually behave. And so that's what I'll talk about first, and then I'll talk about the multi-agent planning. So, learning, driving examples may be easier to look at, right? If you have just data sets, then and you've never seen something, then you have these challenges with distribution mismatch. If you haven't seen all the demonstrations you could potentially get, or you might see somebody doing something wrong. And so what we, instead of just relying on the data, what we do is also include STL specifications in the learning to try and enforce some structure in the behavior of the system. So for example, we would say, okay, you have to first do a downwind, which is this section here, then you have to do a base, and then you have to do a final, and you're not allowed to overfly the field, for example. And so then this constrains what the system can do. And so this was our first approach here is so it predicts the output, but then also has this STL constraint in there to try and guide the search. So so here's an example for planning for this aircraft landing. So it's coming, so the airport is in the center, the aircraft's in the lower left-hand corner, and then the magenta lines are the plans that it's planning. And so you can see these specifications as these rectangles, and then you can see that the aircraft basically follows these specifications. So these are not hard specification because they're also not hard rules by the FAA guidelines. And so it's preferable to follow them, but you can violate them. And so anyway, so the aircraft then follows this type of trajectory. And we can see, if you look at our data set and then trying to see how well does it meet these specifications, then it is better to follow able to follow them, because of course we have these specifications in there. And so now that we have a way to predict what an aircraft can do, we can use that to try and plan for these multiple agents. And so you can think about this this is also called the social navigation problem, and it's essentially very similar to a game. And so the way we solve this problem is using Monte Carlo tree search, where we essentially try to predict our own action, then see what is the action we think that the human would take, and roll this out a couple of times. And then we also have essentially this heuristic at the end that tries to predict what the cost of the final node will be. And so we compared the system in a user study with about 25 pilots, I think. And so we asked them, hey, how risky did you feel? And then we also looked at their flight performance. And so our method was, and we also essentially we did 3 tests. So we had another human pilot. So there's always one human pilot flying, evaluating the system, but that person did not know if it was flying against another human, against our baseline algorithm, or against our improved algorithm. And so and our method was comparable in performance to a human, and also comparable in terms of safety. So now from the air, we'll go to the ground and then look a little bit at, so we looked at this Monte Carlo tree search, but one of the things we have not looked at is like, how do we learn this value for planning, right? And that's often the biggest challenge for planning is, okay, how do you know what is actually valuable? And so you can also think about this another way is, how do you solve the last 10% of the problem? And there's an equivalent for self-driving. Here we'll look at off-road driving, but the challenge is it's relatively good algorithms that solve 90% of the problem, but the last 10% require a lot of tweaking and engineering, and it's often hard to make these trade-offs. So for example, imagine we wanted to drive on the smooth side of the trail without doing manual tweaking. You can also think about this as trying to minimize engineering effort with learning by going from the engineer in the loop to the engineer on the loop, right? So on the left here, we have the system. We try and tweak some values, see what happens, tweak the values, and so on. Instead, ideally, you'd give a design, just get more data, and the system would learn how to behave correctly. And so before we go into detail, I just want to give a little bit of a relationship between reinforcement learning and planning, because sometimes this is considered very different, but there is actually a pretty clear relationship. So for reinforcement learning, you have a little bit of a different terminology, right? So you have a policy, you have a reward signal, sometimes you have a model and value function. So if you don't have a model, you have model-free reinforcement learning. And so, for example, Q-learning would be a model-free reinforcement learning method. So you directly go from a state and action pair to figure out what is the value of this, and then based on the best value, what is the action. If you have a model and a value function, then it becomes more of a planning problem. So in this case, you have a reward function, you have your model, and you have the value function. And so the model tells you to how you go from one state to the next state, and the reward tells you, given a state and action, what is the reward. And the value function, you can think about like an endgame database or a heuristic. And then using a planning algorithm can basically give you the policy. So given this model, what is the next, actually the whole plan, but you can also just get the next action and then replan. So next we'll look at this reward signal, right? Or the cost function. And that's the part that's often very difficult to find in real life. For example, for this off-road driving problem, we might have traversable vegetation, but we also have non-traversable vegetation, where you have traversable trail and non-traversable trail. So it's very difficult to manually define this taxonomy that will work in any situation. And you can see if you try to do this manually, this is what you end up with. So you'd end up with this kind of display, and then a lot of different values that you tweak to get the behavior that you want the robot to have. But then if you go to some new environment, that set of values might look very different. And so one of the things is that humans are pretty good at off-road driving, and so it is actually very quick to collect more data. And so this is the motivation to try and imitate humans, to try and learn where to drive and not to drive. And we can easily get a lot of data just driving around. And so therefore we formulate this problem as an inverse reinforcement learning process. And so we collect a lot of data, and then we post-process this data to figure out what is the map, what are the states, and for the goal we basically use where they went as the goal. And we can get lots of data very quickly. So based on this data, we create this LiDAR map, we extract some map features, and then we learn multiple cost maps. And so we essentially train multiple classifiers to output a cost map. And then we use that ensemble, and so then we sample this cost map, and then use an algorithm called MPPI, which essentially sampling some rollouts. And so again, here, kind of coming back to the beginning, you can think about trajectory libraries and this type of optimization in a similar vein as regular planning algorithms. So anytime you're sampling it, you're not building a tree or a graph, right? Your graph only has, it is a tree or graph, but the root node is always the start point, and there's no connections between these other vertices. So a trajectory you're expanding is only a single chain of vertices. And so here you're testing a set of, let's say, 100 trajectories or some number of trajectories. And then you try comparing that algorithm came up with as the best option compared to how often your expert has driven there, and you're trying to match those frequencies in your learning algorithm. Now for test time, something else you can do is, since we're training multiple cost maps, we can calculate a risk level using conditional value at risk, or C-bar. So we can say, how risky do we want to be given how good our system is at predicting the cost. So if those values all differ, then we have a lot of uncertainty, and so then that C-bar value will be high. And so what that risk value is kind of set by the user. It could also be a value that's that depends on how desperate a robot is. So as you're trying to get somewhere, at some point you might become less risk averse. And then, so if you look at, here's an example. So as we change the C-bar value, you can see that the trail here, this trail stays very certain, but vegetation, for example, becomes more and more uncertain. So if you become risk averse, we will, for example, not go into the grass. And so here's an example of an autonomous ATV where we use this algorithm to drive down a trail. And you can see it makes some of these risk trade-offs where sometimes it will go into grass, but if it doesn't have to, it will stay on the trail. So you can see the goal that it's trying to go to is this MPP, this little yellow sphere, but it's not always visible. So here's the next goal point. And so we can see this, if we use this IRL approach, we can also get a more accurate expert path reconstruction compared to what we, for example, we had a hand-tuned system, what you saw with the sliders before. We tried to do our best before the IRL algorithm, and so that's our baseline. It also helps not only in essentially following the expert better, but also leads to less intervention. So we will, overall, the autonomy system will perform better. And so here you can see that, for example, baseline method is a little slower. I mean, the speed is very similar, but the number of interventions, it's much higher than the IRL method. So to summarize, I gave you a little bit of an introduction of how planning with a time limit kind of drives how you constructed a graph and then how you search that graph with several examples. So one example we looked at was this informative path planning problem where we're trying to figure out, okay, how do we search an area to maximize the information we gain? And then we looked at this exploration problem more and said, okay, how do we know what is the information we could gain by trying to predict the future expected reward of unknown map regions in this kind of indoor exploration situation? And then we kind of switched gears and looked at this flying in shared airspace, and we're looking at more data-driven methods on how do we figure out how humans will behave in the airspace and trying to enable navigation in this shared situation. And lastly, we looked at how do we learn this objective function for planning for safe off-road driving. And so here, was a particular method for planning, but you could apply the same concept for other planning algorithms as well. Okay, thank you.
Okay, thank you. Thanks, Professor, for this very great speech. Okay, I noticed that there is a question from the chatting box, like our student Huo Dongxing asked, what are the commonly used measurements of this your information besides the entropy? Like from his point, signal field is often assumed to be a guessing progress, and he wants to know the advantage and the disadvantage of this assumption.
Right, right. So yeah, so Gaussian process would be another way to represent that information. So depending on how you implement this Gaussian process, it can be somewhat slow to use that to essentially calculate the objective function using a Gaussian process instead. So in our setup, we use essentially a grid, and each cell is assumed to be independent. And so, so that's kind of the advantage there. So in the Gaussian process, the problem would be as we are gathering information with the camera, our inference would start slowing down more and more. So yeah, so it's a little bit, so it depends a little bit on the problem and how many measurements you're expecting, which representation is better.
Okay. I have some offset small questions. Like I do more slime side, and from my experience, it seems like your work mainly on the active slime side. Like you do more path planning on top of the slime result. So my question is that which part do you think is more important in your searching system, like the slime front end, like a trajectory estimation, or mapping, like the slime back end, the whole graph manipulation, or the third side, like a path planner, your high level strategy? Which side is more important for your whole searching strategy?
Right. I mean, I think everything everything needs to work, but I mean, of course, SLAM is often very fundamental, right? So if your SLAM system doesn't work, then your control becomes harder, and then what you can do for your autonomy also becomes more difficult. But I think there is a bigger question. So the way a lot of what I showed is architected assumes that you have a good state estimate, right? You know your position orientation quite well. And so that assumes that the SLAM system works, or GPS, or whatever method you have. But that is in some of the situations, like for example, this subterranean exploration, that is a pretty hard requirement to guarantee that you always have a full state estimate. So there's a question, what are some methods that combine essentially sensor inputs to the control outputs that don't require a full state estimate?
Okay.
So there might be some information, maybe it's difficult to estimate a 6-degree of freedom pose, but maybe you don't need that pose to really control a vehicle or to make topological exploration, for example, work. So I think there's this kind of, I think, often if you do a lot of SLAM stuff, you're like, okay, we have to get the best pose and so on. But I think there's a question also, is that always required? But I mean, yeah, SLAM for sure, is a never-ending problem. It never works good enough. But I mean, I think there's also a lot of questions on the behavior. Like for exploration, for example, it's easy to say, okay, we'll maximize the information gain or something like this, but that is not necessarily what you really want the system to do, right? Your higher level objective is probably something else. It's like, I don't know, find people or something along those lines.
Yeah. Okay. Thank you so much, Professor Scherer. Okay, Professor Zhao. So, can you turn on? Okay, Professor Zhao is here. Yeah. So,
can I turn off the screen sharing? Or?
You can. Can you share? Yeah. Okay.
Let me share my screen here.
Okay. So the time is almost. Okay. Time is good. Then I will give a short introduction of Professor Zhao and. Professor Moju Zhao, he's my old friend in Tokyo University. We were in the same department during our PhD, and he's like 1 year younger than me, and he entered the PhD program 1 year later than me, but got his PhD 1 year earlier than me. After that, I think he received the ICRA Best Paper Award in 2018 for his the Dragon UAV, maybe the best mechanical design, something like that, right? So Professor Zhao, he graduated from one of the most famous humanoids, like JSK, but he has been doing UAV for almost 10 years. And yeah, let's welcome him to give us this talk. Please, Professor Zhao.
Okay, thanks again for having me here. And it's my pleasure to share my topics, my recent works. It's about the modularity in the area of robotics and its applications here. So briefly introduce myself here. I received the PhD degree in the University of Tokyo under the humanoid robotics lab called JSK, but I always doing different things in the area of robots. And right now I'm the assistant professor in the Department of Mechanical Engineering, which is also a different research field, which is mainly about the manufacturing here. But today I want to talk about my main research fields I have been done from my student work is the unique air robot. We call it the articulated or transformable air robot here. So I started with from a two-dimensional model, just like the left video here, from the 2016, and then I developed it into a fully three-dimensional cell, just like this robot, and I call it the Dragon. And this is from the 2018, and I also presenting this robot in the ICRA 2018 here. Okay. So generally speaking, back to the common topics in the aero robotics field, that in my opinion, that I think there are two hot topics here. The first one is the left side here. It's about autonomous maneuvering in the cluttered or the unknown environment, just like the Professor Scherer presented. And this is a typical research example which used the drone to do the fully autonomous flight in the forest here. It's very amazing here. And the right side is another hot stream. I call it the aero manipulation. It is always done by using the coupled arm manipulator in the air robots to perform some high place aero manipulations, such as the inspection in the factory or in the plant. But I was always wondering that is there any strategy or some unique mechanical features which can combine these two amazing ability into one platform. So my answer is the modularity to achieve the versatility in the air robots here. So let's talk about the modularity in the air robots. This research began from 10 years ago. Start from the idea called the distributed flight array, which is very amazing because it can assemble into arbitrary shape and configuration, and also can achieve a very stable flight in the air. But a very critical limit here is that each flight unit only had one propeller, so it cannot fly individually. So you have to move underground and assemble underground and then fly. So after a few years, there's another research in the right side that use the quad rotors like as a flight unit, and it can do the self-assembly and the disassembling in the midair. And another very amazing feature about this work is it can also change its configuration in the air and do some very simple applications such as grasping and transport the object. But I think that those works still, this skill is very interesting and very amazing, but I think there's a lot of potential about the modularity in the air robot to perform highly ability in maneuvering and the manipulation. So my design is focused on the articulated structure here. It can provide the snake-like locomotion and also the arm-like manipulation at the same time. So this is the concept of our articulate air robots. The whole shape is like a snake-like structure, where you can say it's like the human arm-like. So it can provide a very different way for the exploration in the narrow space, just like the snake-like locomotion in the air. And it can also perform very complex manipulation on the air, just like arm manipulators. If you attach some kind of the end effector, such as a hand at the two ends here. So about the development of our real articulated air robots, we have here I summarize all of our transformable air robots here, and those robots can mainly categorize into two types. The first type is we call the two-dimensional model. It's the upper part here, and we call it the AIRS type. It has the joints each length, but all joints had the same direction and also the same direction with the rotors, so it can only do the planar motion here. But we still develop to a lot of types of the AIRS model. We modularize the mechanical or the electrical system, and we also apply some tilt features. We tilt the rotors to have not only have the vertical force, we can also have the lateral force, well, to increase or to enhance the controllability. We also rotate the tilt rotors, well, to have a more control degree freedom for more extensive maneuvering here. Another stream about our robot is development of the three-dimensional model, which is composed with more degree of freedom, not only in the joints but also in the rotors, which can perform the fully three-dimensional transformation or the three-dimensional joint motion in the air. This is called Dragon. And recently we also developed this robot into several kind of different styles. One of it is to achieve the minimum link number with 2 links, and another is we increase the link numbers from 4 to 8, and like a multi-leg structure here. So for all of robots, we made by ourselves, and so we have to use the CAD to design all components and use the 3D printers or to machining by ourselves, and we assembly by ourselves. So all the mechanical design is original here. So besides the mechanical design, we also develop our original internal communication system. This is very important for our multi-link structure. We have to perform very fast and robust communication between the links. So for the board, we also use the CA CAD to design, and we attach the board into the PCB to our multi-links. And there are many two types of the PCB, the MCU board. First is the spinal. It is like kind of the centralized central board, and the other type is called neuron, which is distributed in each links unit. So the internal communication system is done between the spinal and the neuron, which is based on the CAN protocol. It is very fast and very light and also very robust. And inside the MCU board, we also implement the program based on the RTOS, which also guaranteed very robust and light processing here. So those things is a common platform, common layers for all robots. And from here, I'm going to introduce our robots. Not one by one, but first from start Hydras, and then I will going to talk about the Dragon. So let's first talk about the Hydras here. To provide a more clear understanding about our robots, let's start with the dynamics of this articulate air robots here. So generally speaking, for this kind of multi-link structure, we have to write down a very complex and nonlinear dynamic for this floating base, which is really complex, and it's very difficult to use this equation for control, because we have to use lots of the computational resources. Maybe for the humanoid it is possible, but for the air robot we have to use very light or small onboard computer. So we have to simplify or do some approximation for the dynamics here. So here is a very simple but very powerful assumption. We call it the quasi-static assumption. We assume the motion is very slow, so we can ignore the velocity and acceleration of all joints. So then the single rigid body dynamics can be very dominant here. And we can simplify the equation to a centroidal motion here. If the first line is for the translational part, and the second line is the rotational part. So this is the same with the common quadrotors dynamics here. So we can significantly simplify our control system for the real-time control process here. Okay, so for the simplified dynamics here, we have to focus on the centroidal force and the torque. Here is the target we have to generate the proper value here. So here is the relationship between these two terms, the centroidal range, and this is the thrust force from each rotors. The lambda 1 from the lambda n is from the rotor 1 to rotor n here. So you can see there's a linear relationship between these two terms. We can summarize with the allocation matrix here. We call the Q allocation matrix, which is only determined by the geometric states of each rotors. You can see that there are positions about each rotors here. So if can be obtained from the joint angles encoders from the joint servers. So with this Q matrix, we can do some calculate between these two terms here. But one thing we have to focus to know is that this matrix is also influenced by the joint angles here. So the system here is always variant if we change the joint angles. But overall, it can be used with the framework of the general quad rotors. But one thing you have to know is that the system is underactuated here because the rotors, the joints only have the same axis, so the rank of the allocation matrix is always 4 here, which means that we cannot directly use the thrust force to control the position of the x and y. Generally, we have to first to change the orientation of the robot, and then can generate the tilted thrust force and use the tilted thrust force to control the translational horizontal motion here. So this is called the two-loop control structure here. The outer loop here is about the lateral position R and X and Y, which can generate the desired roll and pitch angles. And then we input the desired pitch and angles to control, plus the pitch and roll and angles, we also have the yaw and altitude. For these 4 axes, we use the inner loop to control these terms. And finally, we can generate the desired thrust force lambda here. So for the inner loop, we have designed and proposed several control methodologies, such as the optimal control called LQI, also the adaptive control, the nonlinear MPC, and recently we also considered the vibration issue for our large link model, and we also developed the vibration suppression method to get this more stable flight. Okay, so this is a very typical application used with this Hydrus robot. We use the multi-link to grasp the object. Just, for the grasping, we also have to consider the additional weight, which is also affect the whole centroid motion. And we also have to plan the proper joint angles to guarantee the steady grasping. The left video shows one of the application. One of the style that use the 2 ends to clip the object, the large object, and also pivot it to change the orientation of the object. It is kind of very interesting manipulation. So, and then in the right side, we also use the whole body to contact with the object, which can provide more stable force closure and for the more stable grasping here. So those experiments were performed in the indoor environment, and the position or the orientation of the object is also localized, captured by the motion capture here. But we also evaluate our system in the outdoor environment in the fully autonomous manners here. We use the onboard sensors not only for the self-localization and also for the real-time object detection here. For the computation, we use the onboard computer for localization and detection, and we also use the RGBD sensors to collect the point clouds to detect the object. And the right video shows one of the experiment results we did in our outdoor environment, and the whole system was performed in the autonomous manner with our state machine, and you can see that the robot can detect the object by itself and grasp it, and then pick it and place to the right place. Okay. So based on these results, we also took part in some international robotics challenge. One of it is called MBZ 2020, which is held in Abu Dhabi. There were lots of the team from different universities from the ETH and also the CMU here. And the whole challenge has had three main tasks. The first one is to perform the interception with the fast flying target in fully autonomous style. And the second task is about the pick and place. And the third one is use the air robot to do the firefighting task. And we used our AIRS platform for all tasks. And fortunately, we succeeded to intercept with the flying target in the task 1, and we got the third place in the task 1. And this result also shows that we also have the ability to perform the autonomous maneuvering or the autonomous manipulation with our original platforms. Okay, so about our software and for this platform, the whole software is public in the GitHub here, and not only provides the control methodology, we also provide the drivers to the actuator and the sensors to perform to use our robots here. But also we also provide the simulation system, which is based on the gazebo to perform in the virtual style. We also use the simulation to evaluate our control system, and also design the virtual sensors to also evaluate our perception or the planner method here. So everyone can access to this links and to try with the simulation here. We also provide the AIRS model and also provide the Dragon, and we also have the instruction for how to use this system here. Okay, so the next part is about the Dragon system. It's a fully three-dimensional model. So this is the how we expect. This is the specification about this robot. This robot was composed from 4 links, and the total weight is about 8 kilograms. And currently, the flight time is 3 minutes because the battery is limited, and the max payload is up to 5 kilograms here. For each link unit, we have 2 batteries to provide the power not only for the rotors but also for the gimbal, for the other servers and other computers. And we have a pair of the rotors. We call the dual rotors in each link unit, and this pair of rotors can be also actively vectored. Just like this video, so we have 2 servos to change the direction of the rotors actively. And we also have 2 joints, 2 servos between links to perform the 2 degree of freedom joint motion here. Okay. So to go deeper about this model, we have the dual rotor module, a pair of the rotors which has the same rotor speed but the different rotor direction. We use the same rotor speed to counteract some aerodynamic phenomena such as the drag moment and the gyroscopic moments. Because we have the same rotor speed, we can combine this rotor thrust into one summarized lambda here. Lambda I stands for the sum of the 2 rotors thrust here. And then we have the vectoring axis, the vectoring angles, the phi and the theta to change the direction of the force lambda. So we have the 3-dimensional thrust force like this equation. So this equation is composed from 2 parts. The first part is the scalar part, which means the magnitude of the thrust, and we also have the direction part, it shows the arrow of the rotors. And for the torque from each rotors affects in the center motion. We can also express in the same way the scalar part and also the direction part here. So from all of the rotors, we can summarize the centroidal range from all rotors like this equation, and we can also obtain the similar allocation matrix Q here, but differ from the AIRS model. The allocation matrix here is fully actuated if we have more than 2 links here. But I'm not going to detail about the control allocation. We don't have this enough time here. So the mainstream of the control is similar with the AIRS. First we have to design the target centroidal pose, the position and the orientation of the COG motion, and then based on the quasi-static assumption, we can calculate the target centroidal range, the force and the torque, and with the allocation matrix Q, we can get the desired control input, which is the vectoring angles and thrust force here. So this figure shows the mainstream of the foundation, the control floor. But for such a complex model, we also have to consider lots of the very special issue. One of the issues is the singularity in some special pose, such as the video here. You can see when the robot become totally vertical, some rotors or the whole body can be very fluctuated because of the vectoring angles is unstable here. So here we actually locked the vectoring angles here and to increase the stability here. So we always have a real-time configuration planning to avoid the singularity or to avoid this unstable motion in the flight. And another very important issue, critical issue with this model is the aerodynamic interference, which is always occurs when in the center vertical pose. This is mainly because the downward flow from the upper rotor to the bottom part, it can generate a downward force. It is kind of the interference. So we have to estimate and compensate it in the real time. So this is part of the external range estimation and also the control consumption here. So you can see that the mainstream is very simple here. It's a single stream here, but to perform lots of the special transformation or joint motion, we have to consider a lot of other things, such as the singularity and also the aerodynamic interference. Those parts is kind of the plugins to this mainstream here. Okay, another very important issue about the tasks by this robot is the motion planning here. Just based on the arm manipulator motion, we have the target X in the task space. Generally, the task space is point out to the pose of the end effector X here, and the configuration space stands for the joint angles for the arm manipulators. But for our dragons, it is floating base, so we also have to consider the root pose in the configuration space. So the goal is to first to assign the target, for example, the target and effector X, and then we have to calculate the target joint angles and the root pose in the configured space. This is called the inverse kinematics here. It is very standard in the robotics here. Generally, it is very difficult to get the closed form solution for the inverse kinematics because the F here, the inverse F here is kind of very impossible to get the closed form solution. So we use the differential kinematics to differentiate the relationship and get the Jacobian for linearization and obtain the inverse matrix of the Jacobian, and we can iteratively update C. It is very standard framework for the inverse for the arm robot here. So we apply this framework to our Dragon robot. We use the iterative optimization problem to solve the problem in each iteration and get the optimal delta C and to iteratively update the C. The C stands for the joint angles and also the root pose. And one of the typical application for this motion planning is the motion of the squeeze through the small opening, like a snake-like motion. Okay. So for manipulation, we also have to consider the external range. So also based on the quasi-static assumption, we can get the equilibrium between all force and torque. You can see that we have summarized the joint torque, external range, thrust force, and gravity in a totally linear relationship. So with this relationship, we can calculate the thrust force and joint torque with the target external range. So one of the typical application using for the manipulation is to move a plate away from different directions. So the target force on the end effector is calculated from the equilibrium I showed in the above page. And we also use the differential kinematics framework to calculate the joint angles and the root pose to perform this motion. And recently we have developed, improved our framework for more actual situation. One of it is to operate a valve on the ceiling, which is quite common in the plant, or the factory here. So the Dragon, we use the motion capture to localize the valve, but and then the Dragon calculates the desired pose to approach it, and also generates the sufficient or the proper torque to get us close the valve, and it can gradually rotate the valve, and finally it can totally close the valve, and you can see the smoke finally disappeared from the pipes here. This is quite difficult for very small drones. We have to generate very large torques, and theoretically this Dragon can generate about 10 Newton meters for the torques. And in this situation, the max torque is about max torque is about 2 Newton meters. Okay, so this is our latest work about different types of this Dragon, which is composed from two links. And another very unique feature about this robot is it can perch to the ceiling using the very special aerodynamic effect called the ceiling effect. So it can attach to the ceiling without any factors or magnetic force, only use the aerodynamic, the rotor force here. So with this perching features, the roller can act like a fixed arm manipulator from the ceilings, and to improve the stability about the end effector manipulation. So with this platform, we have achieved the drilling, painting, and also valve operation and near the ceiling here. Okay, so this is our next goal. in this topics. So what is the next level of modularization? Well, in my opinion, the self-assembly and disassembly in the midair. So the next phase, we want to achieve the first achieve the individual flight ability for each unit, and also achieve the self-assembling or the disassembling in the air. So this can help us to to switch the mode for very cluttered or very narrow space. We can also disassemble to the flight units and to go through one by one. And for a very powerful, for the application or manipulation require powerful torque or force, we can assemble and to do some applications such as the valve operation here. So this is our latest work about the assembly and disassembling. And right now we use the quad rotor types, and this is achievement of the fully autonomous self and disassembling here. We not only focus on the mechanical design and the control, we also designed the recovery strategy, which can definitely assemble with each other, and also the transition between the different the model dynamics model here. You can see you can also still get the stability after the assembly, and right now you can disassemble live with each other, and the whole sequence is very stable here. And one of the application is if we have the assemble model, we can sorry, this is the final page here. Well, we can achieve the fully actuated system. So sorry, it is freeze here. So one application about this robot is we can have a fully actuation motion. So we can do the packing hole insertion application. And another application about this robot is we can operate very large valve with the very powerful torque by this assembled model. So I'm very sorry that my slide is freeze, but this is the final page. So thank you for listening.
Okay, thank you. So thank you for this excellent speech. Lots of materials full of good publications. I saw AJR, and AJR. So much.
Thank you for.
Are there any questions from our students? Okay.
Yeah, I'm going to restart my PowerPoint here.
Yeah. So actually, I have a question for my industrial friends. Like, I noticed that from the early beginning, you designed the Dragon robot. The battery is energy power is one of the biggest problem. Yeah. I noticed that that time I heard from you like that robots can fly only 2 or 3 minutes one time. So yeah, that was maybe the year of 2016 or something. So how about now? I mean, from the industrial, there are lots new power design, new battery. There are some, yeah.
It's a very critical comment. Thanks. Still now, the battery is a very big issue, and it is the biggest bottleneck in our application here. Right now, we only have maybe a few minutes for flight by the battery here, but in other strategy, also for some inspection or application in the plant or the implants, we can use the power cable from the ground, which can offer infinite flight time. But yeah, if you want to fly with very high altitude, I think it still is a very big problem. But unfortunately, we are not the battery researchers, so we have to wait for the evolution of the battery. Yeah.
Yeah. So another question, like I know, like you, it's very rare to find a guy like you in our community, like in our community, like you working in the very hard humanoid lab in making this such kind very hard problem, like the UAV are changeable, the shape changing UAV robots. So I think only you can give us some points, like from your talk, like there are very difficult problems on the UAV robots dynamics, the control models, and also we all know the very hard problem from biped walking set. So what are the biggest difference between the biped locomotion dynamics and between this one and the one you said? Like, what is your feeling?
Oh, my feeling is like that for the biped or the humanoid, we only have the joint torque to control itself, maybe. But for the drone, also, especially for our Dragon, we also have additional, the main actuation force is the thrust force. So I think that the total philosophy is different.
Yeah.
And the control system is based on the thrust force, not on the joint torque. This is one of the difference. And the other is the gravity. I think the biggest issue about the drones is that we cannot do the failure because it will crash on the ground.
Yeah.
So the gravity plays a very, very important roles in the whole system. So the whole so how our model or our control is about how to counteract the gravity, and based on that, how we can generate additional force for the manipulation to generate the external range. So,
so there is no supporting polygon in.
That's right, no supporting polygon, not DMP in the air.
But I noticed that there is one video you find a supporting area from the ceiling and
yes,
the brush. It's a very interesting application. So I got this question from here. Like,
thank you for we do our effort to reach the to how to say to decrease the gap between the humanoid and the air robot.
Yeah, I saw your locomotion spider robot, and maybe you can give us another talk about your unit IDR people.
I'm not a professional about the humanoid. It's very narrow.
You are. I think you are. Okay.
Thank you.
I found there is another question from Mr. Liu Chongfeng. So when you are doing the design like this Dragon, and why use that propeller instead of the more common propeller blades? So
yeah, it's a very good question. Just like you point out, the one main purpose is the protection. So actually, in the early stage when we develop it, always do the failure. It's quite a dynamic failure. So for the very simple guard or the protection for the common breath, it's very dangerous for the experiment. So recently we see that the ducted is wholly protects the propeller, so humans cannot touch to the breath directly. This is one of the reasons. And the second is that the ducted fan can increase the force maybe to 20% because of it's just aerodynamic phenomenon on the ducted fan. So it can increase the force. In that way, we can save some power or be more powerful, power efficiently. And the third reason we use for some typical platform like this perching arm, that we have to use the sailing effect. It's just like the, how to say, the suction air between the sailing and the ducted. If we don't have the ducted, we cannot generate the sailing effect. So for this platform, the ducted is how to say, is indispensable. It's necessary. I think there are three reasons we use the ducted. The fourth reason is more, it's cool. It's cool. It's cool than general propellers, I think.
Yeah, cool. Cool is the
cool is maybe the biggest. Yeah.
Okay. So, are there any other questions? I have actually one more question. Like from the last video, I saw you can your newest progress. You can make some assembling.
Oh yes.
Some like a small robot change the joints between this the former one. Like,
oh yes.
So my question is that are there any possibilities to like change the batteries? Like you under flying, you change some styles and with a new part, new joint carrying a new, bigger, heavier cell
like
and come back.
Yeah.
Yeah.
It's a very, very interesting and unique idea. Maybe we'll achieve it in the future.
Okay, so it's possible. Okay,
yeah.
It's possible to try. Okay, yes. Good. So there is a new question. They are some students said they are doing a design like your Dragon model. So
since we can, this is it's also about.
Oh, that is the old question. Okay. So
it's okay.
It's the old question, I think.
Yeah.
Okay. So if there is no more question, I think time is up, and let's thank Professor Zhao and Professor Sebastian again. Very great talk today, and we will end here. And the next talk is also about multi-agent robots. Let's see you next week, next Tuesday. Okay.
Yeah.
Thank you again. Yeah, thank you, Professor Zhao. Thank you, Sebastian.
Thanks for the invitation.
Thank you. Bye bye.
Bye bye.